Okay, so today's plan is just to continue on with Chapter 10, Parametric Equations. Just a reminder, the Unit 2 exam is this week. So again, just like last time, don't wait until the last minute or the last day to take the exam, just in case there's a technical problem, a personal problem, anything like that. Give yourself a bit of margin in case something goes wrong. So that's due, or that's available this week. It's due this coming Sunday. The quote of the day today is kind of a very short quote from Marcus Aurelius from his book Meditations. B1, you might see, Stoicism is kind of in vogue these days. You might see people posting this on their, Facebook profile or Instagram or whatever. And it comes from a phrase that kind of can be roughly translated. Marcus Aurelius was a Roman emperor who wrote in Greek. So this is roughly translated from Greek, something like, stop arguing about what it means to be a good man, be one. So, one interpretation is that sometimes we spend so much time kind of getting the direction right that we never actually take steps in that direction. So we take so much time trying to figure out what it means to be a good man that we never actually be one. We just spend our whole life trying to figure it out. Possibly another, maybe a little more pessimistic interpretation is that it's much more comfortable to sit in, air conditioned or whatever offices debating about what it means to be a good man than to actually, say, okay, well, I probably pretty much intuitively know what it means, and it's not easy to do, but it's, much easier to debate about it than to actually go out and do it. So that could be another interpretation. But with Stoicism becoming more popular these days, Marcus Aurelius and some other Roman philosophers, maybe their quotes might be floating around a little more. Okay, so picking up with parametric equations, just super quick recall. The idea was that we had some relationship between x and y that maybe, for instance, we're thinking of a particle moving in 2D space, something like that. And instead of trying to describe this as y as a function of x or a direct relationship between x and y, we have a third parameter, t. So we're thinking of maybe a ball or something rolling around on a table, or a celestial body moving around. I think I got myself onto the wrong curves there, but anyway, at one of the crosses, I took the wrong path. But anyway, we can think of something moving around in terms of time on, say, a two-dimensional axis or a two-dimensional plane. And we can think of time as a third variable, or t. It doesn't have to be time, but often I just say time as being being a third variable that relates x and y. This gives us much more freedom in the types of curves we can draw, which is a plus. There's no reason that a ball couldn't roll like this or something and not have a nice function of y in terms of x. But this would be a function in terms of t, because at each time I can uniquely identify where the ball is, even if it were to cross its own path or something. I could say at this time it was at that location, at a different time it happened to be at the same location. And sometimes I'm just interested in the time component as well, or the whatever the parameter is representing. And we also mentioned last time that there are occasions when maybe I do end up with a parametric equation parameterized in time. So this is my t variable. Here's x and y. And I look at this and I say, this might be a nice function, y in terms of x. Can I eliminate the parameter? Can I see what the direct relationship is between y and x? Sometimes that's very difficult to do or not really feasible to do, but sometimes it's not too bad to do. And particularly because I know what a lot of graphs y of x look like. If I want to graph the thing, if I'm given the algebraic structure and want to graph it, often eliminating the parameter gets me to a point where I can get kind of a rough graph. And then maybe I can go back and investigate how the parameter t is involved with that graph separately. But I can get kind of the shape of the graph from the y of x information just because I'm used to seeing these types of functions in their graphs a lot more than I'm used to seeing parametric equations in their graphs. So these might all be reasons to eliminate the parameter. Okay, we started looking at this example over here, and we're just going to continue with this one. We had x of t equals a times sine of t, y of t equals a times cosine of t. And again, our goal is to get a relationship between x and y. Could be something like y of x equals, like y equals some function of x. Or perhaps it's an implicit relationship, which it will be here. And this takes a little bit of, I guess, puzzle solving or creativity to eliminate the parameter sometimes. I noticed that x and y are related through sine of t and cosine of t. I can't easily take one of those and make it look like the other one to do some kind of substitution. But maybe I could use Pythagorean identity. X squared plus y squared gives me a squared sine squared t plus cos squared t, or just a squared. This is just 1. So my implicit relation between x and y is x squared plus y squared equals a squared, just a circle. And we might have been able to even guess that from up here, although this looks a little strange. Usually y is associated with sine and x with cosine, and they're kind of flip-flopped here. So we still do get a circle, but maybe when we investigate how the t component comes into play, there might be a little more interesting behavior to take a look at. But I know that the general path this is going to trace out is going to be a circle. And that's my attempt to draw a circle of radius a, centered at 0, 0. So this is the path this is going to trace out as t goes through some interval, maybe 0 to infinity, something like that. So eliminating the parameter allows me to graph the path, but I kind of know that x is oscillatory and y is oscillatory. So as t progresses, I'm just going to go around this circle. I'm not really sure where I start, where I end. I'm not really sure what direction I'm going around the circle either. I know that kind of usually, in some sense, I like to start on the positive x-axis and go around the circle counterclockwise. That's kind of the typical way that we do it in trig and geometry. Is that what's happening here? So let's first decide what t's we're going to look at. And let's look at t's between 0 and 2 pi. This should get us, I think, one trace around the circle, because sine and cosine are both oscillatory functions with period 2 pi. So I think this should get us one loop around the circle, no more, no less. And let's look at some values of t and their x, y coordinates. So when t is 0, I see that x is 0 and y is a times cos of 0, or a. So we actually start here at t equals 0. Which direction do I travel? In other words, as t starts to move up from 0, do I go around the circle counterclockwise, this point moving to the left, Or do I go around clockwise with this point moving to the right? If t is just a little bit above 0, I'll just write that as 0 plus. It's a little above 0. Well, I suppose it depends on what a is, but we're going to have a bigger than 0 here. If t is just a little above 0 and a is positive, then sine is going to be just a little above 0. So x is going to be just a bit above 0. Cosine is going to be just a little below 1. So my y coordinate is going to be just a little below a. So my x is moving in the positive direction. Of course, y is going to go down in either direction, but I'm heading this way. So I'll put a little arrow here. And then I kind of know that I'm going to keep going around that way until I get back. T equals pi might be a good one to look at. Sine of pi, of course, 0. And cosine of pi, -1. So this is going to be at negative a. And then I could probably guess pi over 2 and 3 pi over 2. But of course, sine of pi over 2 is 1. So here's where x equals a. Cosine of pi over 2 is 0. So y equals 0. And then negative a, 0. So I have my path drawn out in black. And then I have overlaid my time information, or my parameter, my t information. A couple of anchor points for t, 0 pi over 2 pi and 3 pi over 2. I think I was saying negative a when I was writing 3 pi over 2. 3 pi over 2, and then of course t equals 2 pi brings me back to where I started. So I overlaid some anchor points as well as the general direction by putting some arrows on there. So I eliminated the parameter, got a graph of the path, incorporated the t information. Let's try to do this in the calculator. So we're going to use the TI-83 to work with. Most TI calculators work basically the same way. If you have a different calculator, it might work a little bit differently. So let's, of course, in the calculator, we can't really use a parameter like a. So let's use the special case, maybe a equals 2, just to work through how to do this in the calculator. So the first thing that I notice is if I go to y equals, in my y equals menu, it's really not set up for graphing parametric equations at all. So I actually have to change what type of plot I want the calculator to do. So if I go down to mode next to second, I have some options in here. I can change, the floating point accuracy. I could change from radians to degrees and so on. But below radians and degrees, I see that I have function, parametric, polar, and sequence. These are 4 different plot types. The default is on function. So we're going to change that. So make sure that you write down somewhere or something how to do this to change it back to normal. So again, we just go into mode, down the function. And so at the end of today, if you go to your physics class or something and want to just graph something normally, you would just pick function, hit enter, and then do second quit to get out of mode. But here we're going to go over 1 to parametric, PAR. Hit enter, so it's selected, and then just second quit to get out of mode. Now if we go to the y equals menu, we see we get a different setup. We have x1 of t and y1 of t. Note that over here on the left, each of these slashes is a different function. So our first function, our first relationship, has an x1 of t component and a y1 of t component. That's our first xy relation, that's our first parametric function. If we wanted to graph a second parametric function on the same picture, we go down to x2 of t and y2 of t as our second parametric function or equation. So here I want x1 of t to be 2 times sine of t. So 2 sine, and then this xt theta n, this variable button, when I click it, instead of putting in an x, it's going to put in a t. Our kind of standard parameter for parametric equations. And then for y of t, I want 2 cos t. Again, I think this is going to be a circle with radius 2, so I'm going to make my window something like -3 to 3 on both axes. Whoops, I started with t. I want to go from -3 to 3 on x min to x max, -3 to 3 y min to y max. That's setting my window. And then for my t's, my times, I want to go from 0 to 2 times pi. So I'll just do 2 times pi. And then the t step, it automatically sets it as this 0.13 number. I don't know where the number comes from, but it usually tends to work out pretty well. If your t step is around 0.1, it's probably going to give you a graph that looks pretty good. This is just the time interval between steps, right? It's just how many points it's going to plot, how it's going to increment t to go around plotting the points and connecting the lines. If we pick this t step of like 1 or something, we get a bunch of like flat sides. And if we pick a t step of like 0.001, it's going to take it forever to draw the graph. So 0.1 seems to usually be a pretty nice choice. And I think I'm ready to just go over to graph. So if I hit graph, I see I get something that looks kind of like a circle. It looks more like an ellipse because my axes, even though my axes are equal from -3 to 3 on both of them, the screen isn't square. Part of me just wonders, like, why didn't they just make the screen square? But I guess back whenever these were first made, the screen was probably the most expensive part of it. And I don't know. It would just be nice if the screen was square. But we can either just deal with it, or we can go to zoom and then just zoom square. Just hit 5. If I have my whole picture, my whole graph in the screen, usually if I just do zoom 5, it kind of stays in the screen and just squares everything up. We'll redraw it for me. And now it looks like a circle of radius 2. The calculator did graph it slowly enough that I could kind of see what was happening. But if I wanted to be really explicit about it, I can come back to my y equals menu, go to the left all the way to the slash to the left of x1 of t. And if I hit enter, I can go through and pick different graph types. So I could have a bold line. I can have a line like this that's an open dot that will kind of traverse the path, but leave behind it a plot of the curve. I can have an open dot that will just traverse the path, that will just go around the circle, but won't actually plot the whole path. Or I could have a dotted line if I was plotting a couple of plots and I wanted to make one solid, one bold, one dotted, so I could tell them apart or something. Let's do just the open dot for now, just to show you what it's like. And I'm going to graph, and you'll have to pay attention pretty closely because it goes pretty quickly. So pay close attention, but when I hit graph, it should go around that circle one time. It's not going as quickly as I thought it was going to, so that's good. So we saw it just traverse the circle. It did not leave behind a path. And again, if I choose the other option with the open circle with like the dash to the left of it, and I graph that, it will leave behind a path. And I like this one because I can see if I traverse exactly once, or if I had done something like, 0 to 2 pi-ish, I would see that open circle keep going. I'd say, oh, okay, maybe I'm traversing like twice. But if t goes from 0 to 2 pi, I can look at that open circle. I get the path traced out, but I also can verify that it was that it went around exactly one time. That actually will be important for some things that we do later to make sure that we're traversing exactly one time, no more, no less. So that's the option that I usually like to use, the circle with the dash next to it. The dash leaves the plot behind so I can see what the plot is. The circle lets me see, do I just keep going and traverse this 3 times? Or if I only traversed it half of a time, I would know that either way because it just wouldn't draw the whole picture. But if I traversed it more than once, I might not know that if I didn't have that circle that could continue on. But in this case, it does seem like t from 0 to 2 pi draws out this circle and traverses it exactly once, starting at 0, 2 in this case, going clockwise, ending back at 0, 2. Okay, so let's look at this example. Here we have a projectile motion model. So we have something like, we have something like a cannon or something here at this is at a particular XY location. The cannonball starts at height h naught. So this might be h equals 0. And the cannonball starts at height h naught. Or maybe I should say y equals 0. And we start at location when t is 0, x is 0. We fire the cannonball and it's going to follow some path. Its path is going to be related to its initial velocity, the initial speed that it comes out of the cannon, as well as the angle of incline. So as the cannon pointed more straight up and down or more sideways. So the greater the initial speed is, the further the ball is going to travel, the higher it's going to travel. And if I started out really flat, as I incline it a little by little, it's also going to travel higher and further. But I think intuitively we kind of understand that after a certain point, if I point it higher, the ball might travel higher, but actually have a shorter horizontal distance. So my paths might look like, for a very flat initial path, something like this, not much horizontal distance on it for its maximum height on the flight path, and not much in vertical distance, or not much vertical height at the maximum point of its flight path, and not much horizontal distance either. If we incline a little more, we get a higher height and greater vertical or greater horizontal distance. I keep switching vertical and horizontal. Incline a little more, we get more horizontal distance and also more vertical distance. If I incline a little more, at some point I get lots of vertical distance and my horizontal distance starts getting shorter. So importantly here, V naught and theta, and therefore V naught cos theta and V naught sine theta are constants. Now, we're not often used to seeing constants written like cosine of theta, but here theta is a constant. It's the angle that we point the cannon when we shoot the cannonball. So cos theta and sine theta are constants, and v naught cos theta and v naught sine theta are constants. So all that we've done is we've taken the initial velocity v naught angle of inclination theta, and we've translated it into a horizontal component and a vertical component. So x of t, we're not using any air resistance here. X of t is v naught cos theta times t. It's the horizontal speed times time. Distance equals rate times time. Y of t, the same thing for our middle term, just the distance equals rate times time term. Initial velocity in the y direction times time. We have an initial height. We started with our cannonball a little bit above the ground. And then we have the influence of gravity, negative 16t squared, negative g over 2t squared. So you might have seen these types of equations in physics before or in other applications, but that's where all these components come from. So let's try to eliminate the parameter t. I see t in 3 places, and I would like to get rid of it. I would like to get y as a function of x. It seems plausible to do that here because these look like just maybe parabolas or something similar. So this is actually not too bad. This is just x equals kt, x equals constant times t, or t equals x over constant. Our constant looks a little sloppy. It's v naught cos theta, but it's just a constant. So t is x over v naught cos theta. I can take this t and plug it into y. So y is negative 16 x over v naught cos theta all squared plus v naught sine theta. And t is x over v naught cos theta. And plus h naught, that doesn't change. If I simplify a little bit, y is negative 16 over v naught squared cos squared theta x squared plus my v naughts divide out here. My initial velocity actually doesn't matter for this part. My initial speed doesn't matter for this part. And I get tan theta times x plus h naught. I see that indeed I have a quadratic relationship between x and y, and it's a quadratic opening down, that negative in front of the coefficient for x squared. So I do see that I get parabolas opening down as my flight paths, again, in the absence of air resistance. Now, what I've lost is the aspect of time, right? If I had, whatever, horse, Trojan horse coming, and I want to shoot it with the cannonball, well, my cannonball actually has to land on it. So I would need some kind of intersection of the paths at a certain time. It's not just enough to say the cannonball will hit or the cannonball will cross the horse's path at some time, but it might be before or later. If I want to actually hit the horse, then I really care about the time component. If I'm just concerned with the flight path, then maybe this would be an easier equation to use. Any questions so far? And then let's look at this example here. I've used theta as the variable. So my parameter here, so sorry for using theta in two different contexts and two different problems back to back, but my parameter connecting x and y here is theta. And I use that because this is the parameter that's often used in this context. Here, x of theta is theta minus sine theta. Y of theta is 1 minus cos theta. And I'm going to lean on the calculator. Whoops, lean on the calculator for this one. So x is theta minus sine theta, or t minus sine t. As an aside, we want to be in radians here. I think that, kind of at this point, anytime you're in calc, you're really thinking in terms of radians, but just to be clear, we're in radians, so check your mode and make sure that you're in radians. But x is t minus sine t. That's why we can have the same thing inside of a sine as outside of the sine. And then y is 1 minus cosine of the variable. Now, I think this is something like 2 pi periodic, but not quite. So I think 0 to 2 pi will get me something of a nice graph. But I do notice that x of theta has just the theta in here explicitly. So as theta goes from 0 to 2 pi, my x coordinate just keeps tracking to the right. Right, as theta increases, the x is just going to keep increasing. Maybe not strictly increasing, we'll see, but we see that this is going to get larger and larger and larger. So we're not going to get something completely cyclic like a circle or an ellipse or something, but maybe we'll get something that's repetitive in nature somehow. So let me go from 0 to 2 pi on t. What do I think my y is going to look like? 1 minus cos theta. Well, cos theta goes between -1 and 1. So I think y is going to be between like 0 and 2 maybe. And what do I think about x? Oops, maybe I think x is going to be, well, when theta is 0, I know that x is 0. So I know I started 0, 0. And probably I'm going to end up at actually x equals 2 pi. Because when theta is 2 pi, I end up at 2 pi minus sine of 2 pi, or just 2 pi. So I want x to go from 0 to 2 pi. And I want y to go from 0 to 2. I think this should give me a pretty nice picture. So that's my window. I'm going to go into my y equals, and since I cleared out these things, I reset my line marker. So I'm going to go through and pick the circle with the line behind it again. Then I'm going to graph. Let's see what it looks like. Okay, it's graphing. And it seems to have stopped right there when theta was 2 pi. So I think it traversed this arc once. But let me zoom square. Zoom 5. Yeah, so it looks like it traverses this arc one time. Now, what would happen if I let theta go from 0 to 4 pi? Is it going to like go back and forth? What's it going to do? We already kind of discussed what we think it's going to do, but let's check. So if I let theta go from 0 to 4 pi, I want to adjust my window. I want to let my x go further out. I don't think y is going to change at all. Y is going to still be in the interval 0 to 2. Right, that cosine of theta is just going to keep going back between -1 and 1. So y is still going to stay in 0 to 2, but x, I think, is going to keep getting bigger. So let's go out to 4 pi here. Let's actually go out to something like 5 pi, just so that we can see that we didn't miss any part of the graph. And maybe we can go from negative pi to 5 pi, let's say, just to confirm that we didn't miss anything. And y, let's go back to 0 to 2. We'll get the graph and then we'll square it up. So there's my one arc. I'm expecting a second arc. There's my second arc. And then we stop there. So it doesn't seem like we missed anything left to right. Let's zoom square, zoom 5. So we get a little better of an idea of what this curve looks like. And that's what we have. And we could probably expect that if we go out to 6 pi, we're just going to get another one of these arcs and so on. So we get this kind of behavior. So this actually has a name. It's called a cycloid. Lots of interesting things about cycloids. One interesting thing is that it's the solution to both the so-called Tadochrone problem and Brachistochrone problem. So the Brachistochrone problem is the question, if I have 2 points and I connect them with some curve, and I imagine having like a ball at this point, I want to release the ball, and under the influence just of gravity, I'm going to time the amount of time that it takes to get from point A to point B. The Brachistochrone problem asks what curve connecting these 2 points will give me the minimum time. Now you might think, what about just a straight line? That gives minimum distance. But if we imagine a straight line, could I make an improvement? Could I just go like down a little bit and then a straight line? Well, sure, if I go down a little bit, then my ball picks up speed really fast in that first tiny increment, and then it's going to cover that. It's basically the same distance as if I just went in a straight line, but I get to cover it with more speed, so that should decrease the time. So it's unclear what curve should minimize the time. It's not just a straight line, because we can do better than just a straight line pretty easily. But what's the most efficient curve? It turns out that it's a cycloid that's just kind of turned upside down. And it also turns out that that Brachistochrone problem is also the so-called Tadochrone problem. That if we connect these 2 points with a cycloid, like this, with an inverted cycloid, then the time that it takes to get from point A to point B is the same time, no matter where A is situated along the curve. So Tadochrone problem, the same time, versus Brachistochrone problem, the shortest time. Brachistochrone problem says, what's the shortest time to get from A to B? Use a cycloid. But the solution to that, the cycloid, has the same time to get from A to B, no matter where you start along the curve. If you start further down here, as opposed to up here, well, on one hand, you have less distance to cover. Okay. But on the other hand, well, it was kind of steeper up here, right? I got to pick up speed more at the beginning when I started further to the left. It was steeper, so I got to pick up more speed, but I had to travel a further distance. If I start down here, I don't get the advantage of picking up a lot of speed at the beginning, but I get to travel a shorter distance. Down here, I pick up very little speed, but I don't have to travel far at all. So this is also the solution to the Todochrome problem. So this turns out to be a cycloid, and it's called a cycloid because if you took a bike wheel and you attach, say, a light to the rim of the bike wheel where it's shining, and if you just rode the bike forward where the wheel was sticking on the ground, right? I mean, not sticking, but where it's not slipping, it's not like sliding on the ground. It's to move forward, the wheel has to rotate. So no slip condition. This light will follow a cycloid. So it'll go from the bottom of the wheel to the top of the wheel back down, and it'll progress left to right in this pattern. Okay, so that's the basic idea of parametric curves. Eliminating the parameter sometimes helps us graph. As a side note, I mean, it's, I think, pretty clear that eliminating the parameter is going to not be very nice here, right? We have a parameter inside of a trig function and outside of a trig function. That's going to be pretty messy. How am I going to get rid of this theta? If this was like, you know, a 2 or something, that's not so bad. I just solve for sine theta, solve for cos theta, square both, add them together. I can use Pythagorean identity. But with the theta outside and inside, this is a transcendental equation. I'm not going to be able to solve this for theta to be able to get y in terms of x. Even though it does seem that y would be a perfectly nice function of x, it's just going to be intractable to get y as a function of x as a nice algebraic structure. Okay, so moving on to 10.2 then, calculus with parametric curves. So if we have a parametric equation, y equals y of t, x equals x of t, in this context, is the y dx, is the derivative even meaningful, and how do we go about finding it? So let's think about this geometrically. We have some parametric function. Here's x and y, and there's some parameter that's tracing out this curve. Then what does the y dx mean? Well, here I have t is the independent variable, and x and y I'm thinking of as like the two dependent variables. So if I have dy dx at some t equals t naught, let's say this point here, what is dy dx? Well, that says I want the slope of the line tangent to the curve. When I increment x by a little bit, locally speaking, what happens to y? Can I draw a tangent line to the curve through this point? Well, sure. I can draw a tangent line to the curve through that point. That's not a problem. Can I find the slope of the tangent line? Yeah, sure. So this is what I want to do. I want to find an algebraic way to figure out the slope of the line tangent to this curve, even if it's kind of a messy curve, at this point xy indicated by t equals t naught. And again, even if we were looking at a point to say at an intersection like this or something, if I just gave you the xy information, you wouldn't know the answer. Is this a positive or a negative tangent line? But because we know the t value, we know which direction we're crossing. So we don't have problems there either. Even if we're crossing, even if we're at an xy point, that happens at different times, we know what time we're at. So therefore, we know which direction we're crossing. We know what it means to be local to that point. It's more clear than if we just had XY information. I'm getting my papers sorted out here. Okay, so how do we find dy dx? Well, I note that I have y equals y of t and x equals x of t. The derivatives I can find easily are dy dt. I can get that. And I can find dx dt. I can get that as well. How do dy dt and dx dt relate to one another via dy dx? Well, by the chain rule. The chain rule, very roughly speaking, says that when I write my derivatives this way, I can kind of roughly think of them as fractions. Right, dy dt equals dy dx times dx dt. This thing I know I can get it just by basic calc 1 on my y equals y of t function. This one I know I can get it a similar way. This is just literally a multiplication now. I mean, these, something over something, that's actually technically notation. But this is literally multiplication. I can just divide through. And I get a formula for dy dx in terms of dy dt and dx dt. Note that this is going to be a function of t. Right? T is the independent variable here. And that is important, again, because our parametric curves can do all kind of crazy things, including cross one another. And if I just had information about x and y, that might lead to some ambiguity. But having information about t, there's a nice functional relationship there. No problems. So that's our formula for the first derivative. And then what about the second derivative? How do we find the second derivative? Well, let's see. Dy dx is d by dx of y, right? That's another way to think about it. It's applying the x differential operator to a function y. But up here, what does that say? That is dy dx is what? D by dt applied to y over dx dt. Okay, so what is the second derivative? It's d by dx of dy dx. So if we follow the pattern here, d by dx of y is d by dt of y over dx dt. So d by dx of dy dx is d by dt of dy dx. Remember, this makes sense because dy dx is a function of t over what? Dx dt. This is, let me just rewrite this. This is the formula for my second derivative. I find the first derivative dy dx. That's a function of t. I then take d by dt of that and then divide by dx dt. Okay. So these are my formulas for the first and second derivatives. All right, so let's look at this last example. We have a little under 10 minutes left. I think we can get through at least most of this. So let's consider this curve. X of t is -3 cos t, y of t is 2 sine t. Let's use the calculator to get a graph of this. So -3 cosine of t and 2 sine of t. And again, I'll switch this to my circle with leaving a trail behind it. My window, I know this is going to be 2 pi periodic, so I'm going to go from 0 to 2 pi. I'll leave my t step at its default of 0.1 or so. I know x is going to go between plus and minus 3. And I know y is going to go between plus and minus 2. I'll graph. I can see I traverse one time, and it's going to be something like a circle. And if I zoom 5 to square it, it actually keeps, I forgot that the calculator has a 3:2 ratio, but it keeps the same aspect ratio. So we see it is indeed an ellipse. And again, let's go back to the graph. We'll regraph it. I think you usually have to change something in the graph for it to regraph it, or in the y equals menu for it to regraph. So I just overwrote the negative with a negative, and I think that will let it regraph just so that I could see where it starts and where it ends. So it looks like it starts on the left side and progresses clockwise. So it seems like this is probably t equals 0, t equals pi over 2, and 3 pi over 2. And we're traversing this direction. So when t equals 2 pi over 3, well, 2/3 pi is going to be between 1/2 pi and pi. So we're somewhere over here. And our tangent line is going to have a negative slope. Can we find dy dx when t is 2 pi over 3? Well, I need to find dy dt. Remember, my formula is dy dt over dx dt. So dy dt is going to be 2 cos t over dx dt. The derivative of -3 cos t is going to be 3 sine t. t equals 2 pi over 3, or that's 2/3 tangent of 2 pi over 3. And since I don't feel like drawing out the triangles and doing all the trig, we're just going to go to the home screen here and get an approximation. Tangent of 2 pi over 3. And we see we get about negative 1.15. Ideally, I probably should go through and get an exact answer here, but we can see it's a negative slope. It seems, could we have a slope of -1 there? That seems perfectly plausible. What about the second question? Computing dy dx for a given xy value. Now, this could be dangerous, right? If we asked a question like this and we picked an xy value like here, well, that's not a well-defined problem. It's not a well-posed problem. It's not enough information. But here at 0, 2, our curve only goes through that point at one time period. We can see dy dx equals 0 visually, but let's confirm that. When xy equals 0, 2, t is going to be pi over 2. So I'm going to find dy dx at pi over 2. Or that's 2/3 tan of pi over 2, just reusing this bit up here. But I know that tangent of pi over 2 is 0. All right, so any questions on anything? I think we'll do the second derivative next time. Yeah, we'll do the second derivative next time. I don't think I can knock that out in 2 minutes. And then we'll answer some similar questions about the projectile motion example. We'll also, I'll have to decide what I'm going to do for the supplemental video this week, but I might put 10.3 and 10.4 in the supplemental video. In fact, I think that's probably what I'll do. So keep an eye for the supplemental video to wrap up chapter 10. I just have to take a look at the course schedule and see where we're at and what I want to put into the supplement. So keep an eye out for the supplemental video this week. And again, just remember that the exam is this week, exam 2. So make sure to get it completed, well before the deadline of this Sunday evening.